All right, welcome back. So we are gonna take a look at another simulation, right? So last time we looked at how to simulate some natural phenomena using forces, right? Gravity and wind, to be specific. This time we're gonna take a closer look at how forces work, right? And what's the sort of correlation between a force and a vector and how they sort of codependent together. Okay, so we're going to be exerting force, and we are going to be, and that force is going to be either attraction or repulsion, right? So we're going to have a source of force, and we're going to have a particle that's going to react to that source of force, either by being attracted to it or being repulsed by it. And we're going to try and model kind of a natural looking system. And in the meantime, we're going to take a very close look at how the how vectors can be very helpful. So we are going to create another particle class, right? So let's do create file, particle.js. So it's already like the third or fourth time that we're creating a particle. So what that means is that we can start sort of reusing some of these particle definitions. So for example, we already know that a particle is supposed to have a constructor. It needs to display and move, right? So I'm literally copying and pasting the constructor, the display, and the move um, methods from the previous example, from the previous particle that we used, right? So just don't forget to open and close the curlies around the class itself, right? So count your curlies, make sure that you can edit and then tidy code to keep your code tidy, right? And then we're gonna actually make maybe fewer assumptions this time. And so let's um, not assign it any velocity in the beginning, right? Let's go with just 0 and 0. And then the radius, we'll make it a little bit larger. Let's have it at radius 20, right? And that's because I do want to have it reasonably well visible, and it's going to be like a single particle on the screen, right? So something that's 40 pixels in diameter should be well visible. The color, though, we can play around with the color. We can do something like random of 2 pi, right? Again, this is going to be an HSB system between, and the hue is going to go between 0 and 2 pi, and the saturation is going to be between 0 and 1, and the brightness is also going to be between 0 and 1. So I'm going to give it the saturation of 0.8 and the brightness of 0.8 just to make it well visible, right? So in terms of what it does and how it behaves, right? The movement is still movement. It still adds the acceleration to the velocity, and it still adds the velocity to the position. That's all fine. And then when it comes to the display, it's also still the same thing. We have no stroke, we have the fill, and we have the drawing of a circle, right? So all of this remains as is. Okay, so let's show our particle. Let's make sure we don't get too far into the code without actually checking how things are working. So let's go save this particle. Let's not forget to add this to our index.html before the sketch so that it actually loads on our web page, right? So let's do particle.js. And then in the sketch, we can make our canvas maybe a little bit larger, something like 600 by 600, right? That should be large enough. And then let's switch the color mode to HSB. 2 pi would be the largest value for the hue, 1 for the saturation, and 1 for the brightness. And I'm going to add one more. One in here, and that's going to be my transparency or opacity, depending on which side you're looking at it. And in other words, alpha channel, right? So it's going to come handy later. I'll show you how we're going to be using this, right? So what that means is that our background, let's make it just 0, right? 0, 0, 0 all across the board. That's just going to be a black background. So all right, so we are going to have a particle, right? So let's make it. Let's create our particle. Something like let my particle, right? So here it is. And then in the setup function, we can do something like my particle, right, equals new particle. So we're invoking the constructor of our particle, right? And so our constructor, if you remember, right here, will ask for the x value and the y value, right? And then, so the defaults are width divided by 5 and 30, or maybe we don't have to provide defaults at all. That's kind of up to you, how you want to set up your particle, right? We can remove it, and then supposedly, depending on how forgiving the system is, you're supposed to get an error if you just create a particle like this, because now you don't have defaults, but we will provide it with some information, say something like width divided by 2 and comma height divided by 2, right? So that will give us the center point, right? And so now all we have to do is just ask our particle. It already exists, right? We've created it, and now all we have to do is just ask our particle to move and display, right? Let's do my particle dot move, my particle dot display. Perfect. So let's see if this works. There we go. We have a particle, random color, it's in the center, and since our acceleration is 0 and velocity is 0, adding 0 to 0 and then adding that to the position means that we're going to stay in the original position, right? So it's not moving, in other words, which I think is kind of obvious. All right, so let's create a force field. So the way I envision a force field, it's going to be a gradient that's going to radiate from my mouse position, right? So, and we can sort of imagine what that looks like if we were to like just sketch it up real quick, right? We can imagine what that would look like. Maybe let's pull up our mirror board and start drawing. Where's my drawing? All right, so we can imagine what the what this force would be, and it's going to be kind of like a fuzzy, blurry blob. The mirror board is reconnecting. I'm going to try to reload it. There we are. So looking maybe something like this, right? So I have like dense center, and then it gets like fuzzier and fuzzier, and it gets like more and more fuzzy on the outside, meaning like there's this kind of like center of energy, and then we have a gradient emanating out from it, right? So one way to do this is to use opacity or transparency, and then just start creating a number of concentric circles and laying one on top of the next, on top of the next, on top of the next. Each one will then start creating more and more and more opacity, right? So the ones on the outside, right, like the outer layer, will be very transparent, and the ones closer to the center would be very opaque. Okay, so that will create the sort of fuzziness that we're looking for to indicate this is where the force emanates from. Okay, so in order to do this, I'm gonna create a new function, right? So I'm gonna imagine it emanating from the mouse position, right? But if at some point I need to emanate it from other places, right, I can just take this function and supply it with a different position on the screen and have it emanate from there, right? So let's do something like this function, right? And let's call it force field. Force field. like that. And so it's going to take two parameters, or I want it to take two parameters. It doesn't have to, right? Since I'm completely making this up, it's up to me. What's it going to take? But I'm going to give it the position, right? So I can supply from the outside the information about where this force is going to emanate from, and then also the radius, right? So how wide do I want my force field to be? Okay. And so since I am going to be going from the outside in, right? So from big to small, in other words, right? That sounds like a for loop, and it sounds like a for loop that we already looked at last time. And that's the for loop that goes from the end of the array towards the beginning, right? So I'm gonna say let I equal to the radius. Well, for loop. Let's do the for loop. For let I equal to the radius. And then for as long as I is greater than 0, right? I don't care about a circle with a radius of 0. There's no point drawing it. I will just go with I minus minus, right? So I'm going to start with the radius, then it's going to be radius minus 1, then radius minus 2, and then depending on how big this radius is, if the radius is 50, then I'm going to go 50 times. If the radius is 3, I'm going to go 3 times, right? And then, so what I'm going to do, I need to figure out the opacity, okay? So this is going to be my value, opacity. And so what I want to do is have this sort of like invert relationship between the opacity, right? Again, this is something that we just drew, right? So the larger the circle, the larger the radius, the more transparency I want. So the opacity has to be lower. If the radius is bigger, the opacity has to be lower. So in other words, if we have like a range representing our radius like this, right? So this is 0, this is full radius. And so we're going to traverse this range. So I'm going to have another range that represents my opacity between 0 and 1. And so basically I want to say when I have full radius, I'm going to go towards 0, right? And when I have 0, I'm going to have 1, opacity of 1, right? And if I'm in the middle, I still want to be in the middle, right? And then it's just going to create this sort of inverted relationship, right? So it's gonna, you can imagine it sort of like taking a sheet of paper like this envelope and just sort of doing like that, right? So the idea is not super complicated, right? And the implementation is even simpler. So all we need to do is we need to correlate different parts of the mapping function, right? So we already looked at the mapping function. We already looked at how to change one range into another range, right? And use a map function for this. And so in this case, we just need to correlate. So this is going to be our sort of range 1. So this is going to be range 1 end, and this is going to be range 1 beginning, right? So if I'm going to begin here, this is going to be then range 2 beginning, right? So I need to correlate the top to the bottom, and range 1 end will have to correlate to range 2 end like that, right? So in other words, when I'm typing in my function, I need to say, let's map the value of I, and it's going to go from radius, right? So the beginning of my first range to 0, the end of my first range. And then the beginning of the second range is going to be actually 0. And the end of the first range is going to be 1, right? Just like we outlined right here. All right, so that's going to give me the opacity that's going to gently decrease. Or no, sorry, gently increase, right? As the radius is decreasing. That's what I meant to say. So I can use this opacity. So I can say fill, not let, fill. So 0 on the hue, right? Let's make it red. Doesn't matter. Force red somehow it all makes sense, right? So 0 0.8, 0 0.8, right? And then the opacity, right? If I wanted to make a nonlinear relationship, right? If I wanted to, so right now, opacity will, as the radius is decreasing, the opacity will increase linearly, right? If I wanted to create a nonlinear relationship, I would need to like create some kind of a curve, right? And so one way to visualize it, and I'm going to introduce you to this new tool that I use very often. It's a Desmos graphing calculator. You can use any graphing calculator, right? So in our case, y is equal to x, right? So, and if we zoom into the range between 1 and 1, right? So that's kind of what we're looking for, right? It's as the, so that's the sort of how the linear relationship works. If I wanted to sort of make a nonlinear relationship, I would have to introduce something like y is equal to x squared, right? So now I have this very nonlinear shape that kind of like starts very gently, but then increases a lot faster, right? If you ever worked in motion graphics, this is easing curves, right? And easing basically describes how you can start slowly and then end faster, and then start slower and then end faster, like go faster and then end slower again, and so on and so forth. There are different shapes to different easing curves. And so if I want something like this, if I want a nonlinear opacity, I need to just make it opacity times itself, right? So that's what it means to be opacity squared. So I'm just gonna say opacity times opacity. Okay, so that's the idea, right? So if I want kind of a nonlinear relationship, and then no stroke, right? I don't want any stroke around any of those circles. No, oops, no stroke. And then let's draw our circle, right? So it's going to be a circle, and then it's going to take the mouse position, so mouse x, mouse y, and then it's going to take I times 2 as its diameter, right? So as I is starting with radius and then decreasing towards 0, it's going to become smaller and smaller and smaller and smaller. Let's see if it works. Okay, well, before I do any of that, I need to say force field. Oh, and wait a second. So we said that I want to supply the position, right? And I want to supply the radius when I'm calling this function. So let's not build in like hard mouse x and mouse y values. Let's do, so position is going to be a vector. So we're going to say position dot x, position dot y, right? When we're running this, when we're creating the circle. And so now we're going to have to create some kind of a vector, right? Let's call it mouse vector, right? So that we can supply it to the force field. Let's do let mouse vector, right? And then we'll, in the beginning, right, we're going to say something like mouse vector is equal to create vector, and we'll create a vector in the position 0, 0. Because honestly, like when you're running your setup, your mouse is going to be in the 0, 0 point anyway, right? But during the draw, I want to start updating that vector, and I want to start set its values to always be the mouse position, right? So I can say something like this: mouse vector dot set. So that allows me to set the values, and I'm going to say mouse x is going to be the x value and mouse y is going to be the y value. So for every frame, it's going to grab my mouse x, put it in the x value of the mouse vector, take the mouse y and put it in the y value of the mouse vector. Why are we doing this? Just so that I could take this mouse vector and then provide it to my force field function, right? And then I need a radius. And the radius should be proportional to my force field, right? So I'm going to have some kind of a force field emanating. And so let's create a variable for my force field, right? We can say something like let force value, right? Let's do force val, right? and then it's gonna be, or we can honestly, like we can it's fine, we'll figure it out. Let's just do something for now. So I know it's going to be a small amount, right? If you remember from the previous videos, the gravity was a very small amount, and the wind was a very small amount, so I want some kind of a small amount. But if I'm gonna use it in order to represent it visually, right, something like 0.5, so half a pixel, is not gonna cut it. So I'm gonna take the small amount, so force value, and I'm going to multiply it by 100, right? So just as a visualization technique to show me, to allow me to represent this force field better. All right, errors. Fantastic. We love errors. What does the error say? Force field, whatever that is, because force field is not defined. Where am I using force field? On line 17, force field. Of course, because I'm typing force filed, and that's a bad mistake. So let's do force field. All right, so I have a force field, and that's emanating. So basically, I want to, every time I go towards the particle, I want it to either start being repulsed by my force field or being attracted to it, right? So kind of like following my force field. So the one simple way to achieve this would be to subtract vectors, right? So let's talk a little bit more about vector math, and let's use the P5. So let's do reference. So p5js.org reference, and let's look at math. So we're going to go to math, calculation, noise, trigonometry, vector. So here are our vectors, right? So we already looked at adding vectors, right? So that's something that we're using in order to move our particle, right? We're adding one vector to another vector. So let's start. We actually also looked at set vector, right? So set vector sets the vectors x, y, and z components, which is what we're doing right here, right? We're setting our mouse vector from the mouse x and mouse y positions. So, but here is subtract. Let's look at what it means to subtract a vector, right? So there's a there is an explanation, right? So subtract can separate, can use separate numbers, blah, 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 and you can use something like v and then give the numbers, or you can do v subtract v2, or there's a static version of subtraction, right? And so you can call it p5 object dot vector object dot subtract. And then you provide v2 and v1, so you'll subtract v2 from v1, right? And it returns a new p5 vector object. So that's something that we want to remember, right? But let's look at what does it mean to subtract one vector from another vector, right? It just simply means that you will get a vector pointing to that other vector, right? So if I'm, notice here, I'm subtracting vector 2 from vector 1. So I'm subtracting blue from red, right? And therefore I have an arrow pointing from red to blue, okay? So this is a really, really useful kind of visualization. In fact, it's so useful that I want to build it into my own example, right? So what I'm gonna do, so they have this like very neat draw arrow function, right? That is kind of has the same exact intent that I had with force field, right? So it draws an arrow just like force field allows me to draw a force field. So I'm gonna borrow it shamelessly. I might add from the example. I'm gonna just put it down here. And so this allows me to now provide the base vector, right? The vector and the color to the arrow, and then it's gonna draw, like give it a certain line and give it a rotation and then a translation and then add a triangle to it, and so it's gonna represent the vector arrow for me, right? So you can see how they're using it. So for example, they have one vector, and so they're supplying the origin vector, which is just a 0, 0 point, right? That's our 0, 0 point, the origin vector to the actual vector point, which is right here, right? And if you remember, the vector fundamentally just stores two values, x and y, and they're always meant to be from 0. So it only makes sense that we're representing it like this, right? So we draw an arrow from 0 point to that x and y value, and that represents our vector in space, and then we just give it a color of some kind, right? So let's do the same thing. Let's do the same thing for us, right? So the first arrow that I want to draw is a from 0 to the position of my particle, right? Let's do that. So right here, I'm gonna say, let's go back. Sorry, I jumped up to the top of the page. So I'm gonna say let origin, right? So I'll just borrow the same strategy, equals create vector, and it's probably not very economical to do this every frame, but it's okay. We have enough resources. This is not a very complicated code. So we can then just say draw arrow, right? And then from origin to my particle dot position, right? Remember, so our particle, here it is, it has a position, which in itself is a vector, which indicates where the particle is, right? So then I can supply the position of my particle to be the end point of my arrow from the origin, and I can give it some color. Red seems good enough. And then I'm gonna do the same thing for my mouse vector, right? So I'm gonna draw arrow from origin to mouse vector, right? And then this one is gonna be green, because why not? And then where we have red and green, then we're gonna have blue, right? So let's see how that works first and foremost, right? Okay, so I have a green arrow and I have a red arrow, and here they are, and they are showing the positions of my particle and my vector, my force field, so to speak. Okay. Okay. So let's now start figuring out how to calculate the force, right? So we have the force amount, and really all we need to do, if that force is acting from the mouse towards the particle, right? So that means I have to subtract the mouse from the particle, right? So yeah, so if you want to point it from red to blue, right? So red, let's say, being the mouse and then blue being the particle, you need to subtract the blue from the red, okay? So there we go. So we're subtracting, and then so that's going to be a force of attraction, and then what we're gonna need to do is, if we want it to go in a different direction, we're just gonna flip its magnitude, right? So let's imagine a situation, right? And just to sort of think through this whole thing visually, right? So I have a particle, and I have a force field, and I have the arrow. Well, let's put the force field at least slightly under angle, so it's a little bit better represented. So here's my force field, and here is the force. So the force is a vector, right? So the length of this vector, the magnitude, represents the amount of force, and the direction will always be towards the particle if it's attraction. Oh no, sorry, if towards the particle. If it's attraction, and no, towards the particle if it's repulsion, and away from the particle if it's attraction, right? So it's going to either push it that way, or it's going to pull it in the opposite direction, right? So this is going to be the pulling. Okay, yes. Sorry. Okay, so what that means is, if I want a vector, and remember our bouncing ball, right, where we represented velocity with a vector, if I want a vector to point to a different direction, all I have to do is just flip its magnitude, right? So I have either the positive number or the negative number, right? And in this case, it's actually really simple. I always want the positive if I want to repulse, and I always want a negative if I want to attract, right? Which is, sorry, the other way, the other way around. But okay, so um, I mean, fundamentally, I hope you're understanding what I'm trying to say, and then let's one way to resolve this conundrum, whether we're attracting or repulsing with the negative or the positive, is to try it out. Okay, so let's try it out. Let's do this. Let's first calculate our force, right? So we're gonna have something like let force be p5 dot vector dot sub. Remember, if you are calling the subtraction this way, right? So as we noticed in the explanation, so we're using a static version, so like this, right? It returns a new p5 object, and it doesn't change the originals. Okay, so let's try this out, right? So if we want to, let's do it again. So if we want to um, point from, so this is our mouse and this is our particle. So we need to subtract the particle from the mouse. Okay, so let's do this. So we are going to say force is equal to my particle dot position, and then mouse vector, right? So that's going to be our force. Let's represent our force, right? So let's set the magnitude of the force to be something that we can actually see, right? So and then draw an arrow, right? So we will draw arrow, right? And the arrow will be pointing from the mouse vector, and then it's going to be pointing to towards the vector, towards the end of the vector that I've just calculated. So force, right? And not just that, let's set the magnitude of the force, and we are going to make it force value, right? That was our value, so 0.5. And just like here with the force value in the field, you want something a little bit bigger, right? So just to make it visible, we'll make it force value times 100, right? Just for visualization purposes. And then let's make it blue. Okay, let's see. Ooh, errors. Love errors. Let's figure it out. So it says color was expecting a number, but received a bound something instead. So, oh yes. So this blue needs to be in quotation marks because it's a CSS color, of course. All right. So here we go. We have a force that's acting towards our particle. This arrow is always facing our particle, right? So, and the amount of the force that's being exerted is actually proportional to the force value, because I am setting the magnitude of this vector to be force value, but just times 100, again, for visualization purposes. Otherwise, you would never be able to see an arrow that's 0.5 pixels, 0.5 pixels long, right? So that's all great. So now we actually need to, this is all just visualization, right? Now we need to actually make it work, make it act on a particle, right? So I am going to say something like this, right? So I want, so I'm going to suspend the disbelief. I'm creating an approximation of a world, right? And so I'm gonna suspend parts of the physics and implement other parts of the physics. So I'm gonna pretend that there's no force of friction. I'm going to pretend that basically no other forces are acting on this particle except for one, the force emanating from my force field, right? Kind of like a very, very sort of limited representation of physics, but here we are, right? That's literally what simulation is. You take just one component of reality and you look at it specifically in that, specifically at that component and disregard everything else, right? So, first, let's set the magnitude, right, of our force field, right, of our force vector. So we're gonna say something like, yeah, let's do this here, right? So let's remove this, and so we have the force field, we have the force, we're good to go. We can say force dot set magnitude to be the force value, right? And then so because originally it was just however far the mouse is from the particle, right? That was the vector. If you remember, this is kind of like how it works here. It covers the entire distance, the subtraction of two vectors. But I don't want to be that. I don't want my force to be that huge. I always want to control the amount of force I'm exerting, right? And feel free to play around, for example, with increasing or decreasing force depending on the distance between the particles. That could be always very interesting. But in this case, I just want to exert always a static force that comes from this force value, right? So I'm going to set the magnitude to be a force value. And then I am going to, since I'm suspending the disbelief, or sorry, suspending parts of physics and implementing other parts of physics. So the fact that I only want this one force to act on my particle simply means that my particle dot acceleration is going to be that force, right? So it's just going to be equal to force. That should be it. Let's see if it worked. Ooh, something didn't work. Oh, because, of course, as always, it is a spelling issue. Okay, there we go. We are repulsing our particle. We're repulsing it pretty effectively, right? So here it is being very, very repulsed, right? And so it's getting more and more and more repulsed and further away. So great. That's pretty good. There are a couple of things that you can do in order to um, um, make it a little bit more useful for us. So, for example, actually, before we make it more useful, let's see if we can attract. What if I set it to the negative, right? Ooh, yeah, hello. This is how gravity works. You have particles rotating around other particles. So this particle is always kind of like trying to get as close as it can to the force, right? And so at some point, it's just gonna start like circling and rotating around it, and it's kind of fun to watch. But okay, so we have the mechanism, right? So let's make it a little bit more useful. So first of all, where like if I am attracting the particle, right, I actually don't care if it goes off of bounds every once in a while because I know that it's going to come back because it's always going to be attracted. But if I'm repulsing it, right, I want to make sure that it stays within the bounds. Okay, so that means that I'm going to have this bouncing mechanism, bouncing function that is going to be contingent on external circumstances, right? So in the previous cases, when we had the bouncing ball on the field, we made the bouncing part of the movement. I am not necessarily going to do that, right? I am going to make bouncing its own thing, okay? So I'm going to go and give it the ability to bounce. So let's go bounce, but it's going to be its own thing, right? So fundamentally, it doesn't have to be a part of the movement. I can always just say bounce. I can always call bounce in some cases and not in others, and so I will let my particle bounce in some cases and not in others. Look at this thing go. But anyway, so the way to write the bouncing mechanism should be very familiar by now, right? So we're gonna say if this dot position dot x, right, minus this dot radius is less or equal to 0, right? Or where's my or? Here it is. This dot position dot x plus this dot radius is greater or equal to width, right? So if we are at the left edge or if we're at the right edge, all we need to do is just flip the velocity, right? So this dot the velocity times equal -1. Okay. And we can do the same exact thing for the y axis, right? So if this position dot y minus the radius is less or equal to 0, or this position dot y plus the radius is greater or equal to height, right? This velocity dot y, and let's make sure that this is velocity dot x, right? So velocity dot x flips if we're touching the right or left edges, and velocity dot y flips if we're touching the top or the bottom edges, okay? All right, that's cool. So we can start bouncing things, right? Let's see. So I also want to make it contingent. So I'm going to start making a bit of a UI for my simulation, right? So one typical sort of built-in element for toggling things in HTML is radio buttons, right? So radio buttons will, only one of them will be engaged and all the others will be disengaged. So if I have two radio buttons, one will always be on and the other one off. And if I press the other one, it's gonna sort of start doing thing, like kind of this type of stuff, toggle, right? Because that's how the buttons worked on old radio station programming, on old radios when programming radio stations. There you go, right? So let's create, so we added the bouncing, and then so we're gonna have some kind of a contingent condition that we'll be able to control from our radio buttons. So we can say something like if something, right, pushing, right, let's put it here, if pushing doesn't exist yet, and we're gonna create some kind of a condition, but we're gonna say, so if pushing, we're gonna set the force to set magnitude from force value, and then otherwise if pulling, right, so else it's gonna be the minus the force value, like we're doing right now, right? So there we go. Okay, so this is going to be the case of pulling. So now let's add the interface. So if you remember, if you go into the reference and you look at DOM, document object model, right? So your HTML structure. So here is an example on how to create a radio button, right? So you go, where is it? Create radio. Here it is, right? So here's some examples. So there are 3 radio buttons in this case. I only need 2. Right? So, but fundamentally, you need to create a radio button, right? Set its position, set its size, set the options, and set the default selected value. Okay, so that's what I'm gonna do. Let's go back to our sketch. And right here, I like to do this separate UI thing, right? And then we're gonna do something like this. We're gonna say let mode toggle, right? Toggle, right? So this is just going to be a way for us to toggle our mode from pushing to pulling, okay? And then in our in our setup right here, we again going to create a UI component, and then let's do this, right? So we're going to say mode toggle, and we're going to be using it a lot, so I'm just going to copy and start pasting it. Mode toggle dot mode toggle equals, sorry, create radio, right? And then we're going to say mode toggle dot position, and I want it like under my sketch, right? So it's going to be, let's say, 0 on the X and height plus 20 pixels, right? Something like that. And then mode toggle dot size is going to be how big is the area that we're allocating for this control, like maybe let's say 60 pixels. And then we'll do mode toggle dot option. And so one option is going to be, let's say, push, and the other one, I'm just going to start copying and pasting, is going to be pull, right? And then let's get the one that's going to be selected by default. Let's call it selected push, right? So it's fine. It doesn't matter which one is selected. And so then we can say, okay, so it's not just some kind of like pretend value called pushing, right? It's actually going to be the value of our selection. So we'll say mode toggle dot value. If it's equal to push, we are going to push the particle away. And not only will we push the particle away, we're also going to bounce it, right? But not just dot bounce. It's going to be my particle dot bounce, right? So it's the particle that's going to bounce, not anything else. Okay, let's see if this works. Boom, boom. Okay, so here is a good example of an artifact. So you saw the particle kind of jittering on the edge and then just disappearing. And right now it's off the edge and it's God knows where, right? So that's an issue I think we've encountered in one of our previous videos, right? Where I challenged you to think about how to resolve this. Well, finally, we're going to get to the resolution of it, right? So fundamentally, the reason why it happens, and I'm going to try and see if I can do this again. There you go. It's going off the top edge now. The reason why it happens fundamentally is because of this. So let's go over here. Let's draw this out. All right. So the reason why it happens for the fourth time. So here's the edge. So if you remember, when the particle is touching the edge, or maybe even a little exceeding it, if our velocity was negative, let's say it's 0, right? So it's the left edge. So if our velocity was, let's say, -4 going towards the edge, it's going to become +4, right? And we're going to move away by 4 pixels from the edge. Okay, but what if a situation happens where our velocity is actually not set precisely, but is dependent on the force, on the acceleration, on a whole bunch of factors. And so what happens, it kind of like jumps through, right? And then we're saying, okay, so it was -4, right? So we're going to flip it to 4. So it jumps through pretty far. And then, so if the edge was, let's say, now -10, right? So if our, let's say, the radius of our particle is like 5 pixels or something like that. So the radius is -10. If it becomes 4, it pushes it back. And now the radius is -10. -10 plus 4 is going to be -6. And then, so -6, and then we're going to check, is the edge less or equal to 0, right? Because that's the condition. And we're going to say, oh yeah, well, it's still less or equal to 0. So let's flip our velocity again from 4 to -4 again, and back it's pushed to -10, right? And then we flip it again to 4, and back it's pushed to -6. And here it will get stuck between -10 and -6 and -10 and -6, because we're keep flipping this velocity positive to negative, negative to positive, but that's not enough to push it away from the edge, right? And if that velocity is further being affected by, let's say, acceleration or something like this, right? Like some external forces, then at some point it might even get pushed through and completely disappear, despite the fact that we were asking it to bounce. Okay, so one way to fix it, something relatively simple and maybe even crude to some extent, but quite effective, would be to say, well, how about this, right? Whenever the edge of my particle is, or whenever my particle is on the edge or even beyond it, make it forcefully be touching the edge, right? So on the other side of the edge. So if it's going beyond, it will just forcefully yank it and keep it um, on the sketch, on the screen. Okay, so not a particularly difficult thing to say, not a particularly elegant thing to say either, but it's effective. It works, and it makes it seem like it just doesn't go through the edges, right? So it would look something like this, right? We would say if this dot position dot x minus this dot radius, right? So again, if it's the left edge of my screen is the 0, and the left edge of my particle is going to be its position x minus its radius, right? So if it's less than 0, if the left edge of my particle is less than the left edge of my screen, then we just simply going to say this dot position dot x is equal to this dot radius. So it's going to be just the right amount so that its edge is touching the screen, right? Touching the edge of the screen. So its position B is going to be its radius away from 0. Okay. So in other words, something like, we could say 0 plus the radius, right? So its edge plus the radius, but 0 plus the radius is just the same as saying this radius. So on the other side, right, we would say if this dot position dot x plus this dot radius is greater than width, right? If we're exceeding our width, and I don't know what this is, I want to say plus, then we're just going to say that this dot position dot x is equal to width minus this dot radius. So we're going to push it forcefully to the left from the right edge by its radius. So it's going to be sitting the radius amount from the left edge. Okay, and we can say the same exact thing about the y-axis, right? So if the position y minus the radius, then position y is equal to radius. And if the position y plus the radius is greater than height, then position y is equal to height, right? And I'm adding all of this to my bounce method, right? So to me, this is all part of bouncing. Accounting for the bouncing errors is also bouncing, okay? All right, so let's stop this. Let's see if this works better. All right, so it seems to exert a very, very strong force, right? So it's almost like a naturally strong force. It's not that much fun, right? But it's not going off of the edges, right? I can actually see it going through for like half a frame or something, but then it always returns, right? And here it is. It's always bouncing, 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 bouncing. Okay, so it doesn't look particularly natural, and so this is where I'm gonna fudge things a little bit and kind of like finagle with my simulation, and I'm gonna say if I'm pushing, I'm just gonna multiply it by 0. I'm just gonna use 10% of the force. Otherwise, the pushing is too hard. I don't like it. This is a lot more fun, honestly, right? And then, but then when I'm pulling, okay, so we're no longer bouncing, but the pulling force seems to be fine, right? The pulling force seems to be doing all right? And then let's go start pushing again, pushing. Right. So I like this a lot better, even though um, it's not exactly quite correct, right? But it just looks better. Okay, so next order of business, let's add some more useful things into the interface. So first of all, I like the ability to see the vectors, but I might not want to do it all the time. So what I'm going to do, I'm going to use the mouse pressed option. So basically, I'm going to say when my mouse is pressed, I'm going to show the arrows. Otherwise, I'm just not, right? So I'm going to say if mouse is pressed, and then open, and then I'm gonna indent all of these guys and close, right? So here we go, right? So now I'm just gonna exert some pushing and pulling forces, and then if I press my mouse button, I can actually see how my arrows are working out. Yep. But anyway, all right, so that's one thing. And then another thing, I already have the kind of interface component that allows me to push versus pull. And wouldn't it be great if I also had an interface component that allows me to set the amount of force, right? So let's give it let force amount, right? So that's going to be another UI component and a slider. Sounds like something quite reasonable for this task. We've already done a slider, so this should be a familiar enterprise for you, right? So let's do right here after the mouse toggle. We're going to say force amount is create slider. So in order to create a slider, we are giving it the smallest value. Let's make it 0.01. The largest value, let's make it 1, right? What's going to be the default value? And the default value right now is 0.5. So let's use 0.5, right? That's going to be our default value. We can add more, we can add less. And then the increment, right? The resolution of steps between the adjustments. So that's also going to be 0.01. So 1% basically of 1. Okay. All right, so just like with the menu toggle, we need to set its position. So force amount is going to be equal to position 100 and then height plus 20. So basically what I'm saying is going to be on the same level as my radio button, but 100 pixels over. Since the radio button is at 0, my force amount is going to be at 100. And then force amount dot size, it's going to be something like 300 pixels. That seems reasonable. Okay, and so now what we need to do is we need to, when we're setting the magnitude, right? So this force value needs to be derived from the value of the force amount, right? So right here, after I calculate the force and draw the force field, I can do something like let's do, oh, actually no, let's do it before, because the force value, I'm going to use it to draw the field, right? So let's do it before. So force value is equal to force amount dot value, right? And then after that, I can use this force value to draw the force field, and I can use it to set the magnitude and to set the magnitude over here, and so on and so forth, right? So fantastic. So let's see how that works out. Ooh, what happened? There's an error. Position is not defined. What did I do? Its position is not defined. I misspelled it. Oh, force amount dot position, of course. Typical. All right, so there we go. We're bouncing, and this is the force that we're exerting. Come on, move. And then we can start pulling and have like a very strong pull. So it's just going to start like a massive pull. There we go. All right, so that's about it. Um, See what else you can do with it. I think one very interesting thing would be to have the force be proportional to the distance, right? That's kind of how it works in the physical world, right? If you remember Newton's laws, see if you can code that in, right? See if you can do other stuff. See if you can create maybe a better representation of the force field or something like this. Try to experiment with it a little bit, and yeah, as always, don't forget to have fun with it. All right, I'll see you next time. Bye.